In this video, I'm going to talk about Kirchhoff's voltage law. It's based on the principle of conservation of electrostatic field in a closed loop. The law states that the sum of voltages in a closed loop equals zero. Let's explain that with a simple circuit. We have a voltage source and two resistances in this circuit. Now, if I'm going to traverse this circuit, Kirchhoff's voltage law states that the sum of voltages in this closed loop equals zero. Let's say the voltage across the voltage source is V sub 0, the voltage across resistance 1 is V1, and the voltage across resistance 2 is V2. Now, we have a little bit of a convention here, and I'm going to explain that intuitively. What happens when we move from the negative terminal to the positive terminal of a voltage source? There is going to be a gain in potential, and therefore the voltage is going to have a positive sign. When current flows through a resistor, energy is dissipated, there's a drop in potential, therefore there's a negative voltage when current flows through a resistor. Now, if we were to apply this convention to the circuit and we were moving in this counterclockwise direction, what would happen is we're moving from the negative terminal of the battery to the positive terminal of the battery. So we have a plus V sub 0. Current flows through the resistor. Energy is dissipated. We have a negative V1. There is a further drop in potential when the current flows further down the circuit. So there's a negative V2. And according to Kirchhoff's voltage law, let's say KVL because Kirchhoff's kind of a hard name to pronounce, we're going to have the sum of the voltages in the closed loop equals zero. Let me explain that better with a further example. Let's say we have a voltage source and we have two resistances attached in parallel to the voltage source. Now, let's attach a value, say 20 volts. We have two resistances in parallel. Let's say there are 20 ohms and 40 ohms respectively. Now, if we were to apply KVL or Kirchhoff's voltage law, there's going to be three loops that we consider. This is the first loop. This one right here is the second loop. And then there's one loop here. And we want to write KVL for all three loops. Let's say, or start with loop 1. So in loop 1, let's call this voltage across the 20 ohm resistor V1 and the voltage across the 40 ohm resistor V2. So in loop 1, according to KVL, we are moving in a counterclockwise direction. There is a gain in potential as we move across the voltage source. So it's plus 20 volts. And there's a drop in potential as we move across the resistor. So negative V1. And according to the law, the sum of the voltages equals 0. Therefore, 20 volts minus V1 equals 0. V1 is equal to 20 volts. Now, in loop 2, what happens is that the current is flowing in a counterclockwise direction. When you're moving through voltage 2, you have energy that's dissipated. There's a drop in potential. And when you're moving through voltage 1, and you're moving counterclockwise, remember, you have a positive V1 that's actually just negative of negative V1, and the sum of the voltages equals 0. Therefore, we have V1 equals V2. Now, applying KVL to loop 3, we get plus 20 volts. There's a gain in potential as we move across the positive voltage source, and there's a drop in potential when we move across the 40 ohm resistor, so there's a negative V2, and this equals 0 because the sum of the voltages in a closed loop equals 0. So we get V2 is equal to 20 volts. Now, V1 is 20 volts, V2 is 20 volts. If we were to calculate the current that flows through the resistor, that's I1, we could use Ohm's law. That's I1 is equal to V1 over R1, 20 volts by 20 ohms, 1 ampere. We could use Ohm's law again to find I2. I2 is V2 over R2, which is 20 volts by 40 ohms, which is 0.5 ampere. Therefore, the current, by using the current law, the current that comes out from the battery is I1 plus I2, which is 1.5 amps.